FGM-3 magnetometer shield for Arduino. Electrical specifications. I've got a current meter in series with the power supply, which is just a 9-volt 500 milliamp wall adapter transformer. I've got the smaller meter measuring the current draw. I've got the larger meter measuring voltage rails with that. The oscilloscope's measuring the frequency output after it goes through the Schmitt trigger. And I was expecting a perfect square wave, and I think this is probably more to do with my scope probe than what the signal actually looks like. It is stable, it does react to the field. With everything powered up and without a Bluetooth radio, when the board is idle, it's drawing right at 85 milliamp until it goes to transmit, which it does. It transmits data every 10 seconds. It takes a frequency reading each second. So every time that comparator that's counting the frequencies is turned on, or when the data is being sent over the USB port, you'll see it go from 85 to 150. And I have tested this with a Bluetooth radio. I'm using a JY MCU. It's just a serial port service that sends serial RS-232 data over Bluetooth. The radio seems to consume about 40 milliamp. So in any state, if it was idle, with the Bluetooth, the current draw is 125 milliamp. While it's transmitting, it is 190 milliamp. Everything on the Arduino microcontroller is running off of its internal regulation and 5-volt rail, which is staying at a solid 5 volt. Now that rail is only for the components that are on the microcontroller. The FGM breadboard is here with all of its components, and when it's done, let me get a prototype shield. Everything that's on this board will have to be squeezed onto a shield that is exactly this size, with the stackable headers so that you have access to some of the pins, especially the frequency output and the analog output. So you could connect this to a XY plotter or a frequency counter. So the finished product will have, it'll be a 2-layer board using a modular RJ45 jack to interface between this board and the FGM sensor, which will have its own little interface board that contains an identical modular jack with indicator LEDs and its own power regulation. So what will happen is when this thing, there's an auto power select on the Arduino, and it looks at the voltage if you've got both your USB and your wall adapter attached, it will pick the higher of the two voltages. So in order for this to work, you cannot run it off of USB power alone. You must have the supply attached as well. The USB is not meant to power it, it's only for communication. In Bluetooth mode, you would not even need the USB cable. So because of that feature, the VN pin on the Arduino power rail gives me the supply voltage after its protection diode, its reverse protection diode, which does cause a small voltage drop. I typically get about 7.5 volt to 8 volt off of a 9 volt input, and that is before any regulation. So there are two regulators on the breadboard. They're both, this is a 7805 in a 220 package, and this is similar to a 7805, but it's a different part number, and it is a surface mount component. Both handle 1 amp. This is representative of the regulator that will be on the interface board. So you will basically connect an ordinary Ethernet Cat5 cable into a modular jack like this, except the ones that we will be using will have a LED on each side, one for connectivity status and the other for a transmit data LED. So the green blinking LED you see there, I've just got that there now as my TX LED, but in the end this jack will be on the shield, and you'll have connectivity with the yellow LED on the modular jack, and your transmit data activity will be the green LED. And then you would just plug your Cat5 up to probably 150 feet. I'm actually going to test this with 200 feet, which would be probably the worst case scenario. But for most applications, 50 feet will probably be fine. And then the other end of the RJ45 will plug into the FGM interface board, which will also have its own connectivity indicator light. This is a 3-pin sensor. There's a 4th pin for a feedback coil that's not used. So you have this sensor will plug directly into a right angle female pin header on the interface board. It has 2 mounting holes on the PCB to secure it, and once you plug in your Cat5 cable, it'll receive its 9 to 12 volt supply, regulate it at the sensor, send back a power on connectivity 5 volt logic level, and send back its frequency, which is directly proportional to the field. On the first batch of interface boards, I had marked which way should be east and west. These have a sensitive axis. This is the easy axis. For proper operation, it needs to be oriented east-west along its long sensitive axis. But the first 3 boards I have coming back, I've got my east and west orientation backwards, so that'll be changed on the next batch of boards. Actually, the terminal end of the sensor should be facing exactly east if you want a positive bias field reading. If you turn it around, it'll still work, but you'll be reading an opposite field polarity. So the recommendation would be to preferably bury the sensor sealed in a PVC pipe. And I've got a compass up here somewhere. There it is. So I'm gauging roughly east and west, and I've got my sensor aligned east-west with the terminals facing east, the other end facing due west. This transmits data. The chip is updated every 8 seconds. The main ASIC that converts a frequency into a byte, and then that is sent to an A to D converter. And we'll get to why we have all these options in a minute. The signal is conditioned for long cable lengths with a Schmitt trigger, and we have a parallel to serial shift register to save a lot of pins on the microcontroller and to grab that byte and then transmit it serially to the microcontroller. So when it comes to software, I will exit out of this for a minute. These will come with the software on CD-ROM and the firmware already loaded. And I'll do a better video presentation of the software at a later time. This is written in Processing 2.0. So when you first install the application, you won't see this happen now, but when you first install the application, the first thing it'll do is it'll want to go out and locate the microcontroller, because it could be on any USB port, and so it'll prompt you to just click the mouse, which will initiate a COM port search for the device. And that, along with a lot of other user settings, are saved into a config file. But unless anything changes, that only happens once. So when I run this, I'm going to get the splash screen. And unless a reset is required, we should connect. And I'll set the tripod down and go over some of the software if my tripod cooperates. I may not get the entire screen, but that's okay. Okay, so we connected, and I know this because of down in the lower right corner is your user interface and your raw data. You've got a Bluetooth, you've got a USB icon with a check mark. Next to that, you've got a power monitor. So if it drops below 5 volt, it will notify you. The battery will turn red. So we've got good regulation, 5 volt, and we are connected to USB, which is what the icon is for. If there was a communication error, you would see a USB icon with an X. If you were in Bluetooth mode, you would see a Bluetooth icon with either a check or an X. But let's start at the top. You can hit the F3 key on the keyboard at any time and set your general location, and I also include my latitude and longitude, and it converts any Windows system time into universal time. So that timestamp on the left upper right is when the plot began. The plot runs for 24 hours and it is a variation style plot. It starts out with a 0 reference, and throughout the day we'll plot the changes in nanotesla above or below the 0 reference. Positioning your cursor inside the graph area will give you, like if I want to know what this value is here, just put my mouse over it and you've got the time and you've got the value. There's 4 sensitivity settings, all software controlled. For geomagnetic storm monitoring, I would suggest the highest, which is a range from 150 to minus 150 nanotesla. At the bottom right is a K index meter, which is calculated every 3 hours. And if you don't know what the K index is, you can find more about that on NOAA's website. But it's calculated every 3 hours. It's a geomagnetic storm indexing number system. Right above your buttons, you've got your raw data. So you've got your frequency coming in, which is, if not directly, almost directly absolute proportional to the field in nanoteslas. I've got another station set up. It's measuring right at 52 microteslas. It's quite a bit noisier out here, so I'm reading 65.66 microteslas. And it gives you your A to D value, your analog value, and the digital value coming off of the ASIC. And one other thing, you've got a real-time clock that ticks away under your sensitivity. The buttons down below, the first button just takes a screenshot and saves that into a snapshot folder. And if you want to know what any of the buttons do, you just roll over them and it'll tell you what these buttons do. The second button will reset the plot. It'll zero out the sensor and wipe the graph clean and start at the current time. Start a brand new plot. On the fly, you can choose to plot either the analog or the digital values, which is what that button is for. And you can change this on the fly. There's advantages to both. I'll do it right now as a matter of fact. So right now I'm taking the analog output and that's what I'm plotting. So if I just click that, I've switched to digital input. So it'll be plotting the digital values. Because the output of the ASIC is 8 bits, you've got a value from 0 to 255. The microcontroller has a 10-bit analog to digital converter, which essentially doubles your resolution, but it's a little bit jumpier. So your values may sway up and down by a few digits. Whereas the digital input, you don't have quite as much headroom, but the values are more consistent. So they work equally as well. It's just a matter of preference. The USB icon naturally is if you want to communicate in USB mode. If you have the optional Bluetooth radio, you can connect by clicking the Bluetooth icon. Clicking the sensitivity will change the sensitivity of the ASIC, and there's 4 settings. The lowest, I'll click it right now. Okay, so that set it to its lowest sensitivity, which is plus or minus 1000 nanotesla. Now for geomagnetic storm monitoring, this is not ideal because you're not going to see a big change.